This lesson is all about sketching gradient functions correctly. Let's start off with defining a stationary point. So a stationary point is a point where the derivative of the function is equal to 0. So if you were to draw a gradient at that point, the gradient at that point would be equal to 0. It can be one of three things. It can be a local minimum, a local maximum, or a stationary point of inflection. So it's defined to be one of these three things. And it also can be defined to be points where the function is neither increasing or decreasing. So let's look at the three different cases you can have for a stationary point. So you can have a stationary point here, which is a local minimum. Now, if you look at the gradient at the minimum point is 0. Now, before the local minimum, you can see if you draw a tangent to the curve, it's negative. And after the local minimum, it's positive. So in a local minimum, the gradient is negative 0, then positive. Okay, if you have to think of it another way, is i.e. function changes from decreasing to increasing. Okay, let's look at the local maximum, how that's different. So at local maximum, you know the gradient is 0. Now before it, you can see if I draw a tangent to the curve, it's positive, and after it, it's negative. So the gradient is positive 0, then negative, i.e. function is changing from increasing to decreasing. Okay, a stationary point of inflections can be of one of two types. So it can be, obviously at the stationary point of inflection, the gradient is 0. In the first case, you can see if you draw tangents to the curve before the point of inflection, it's positive on either side. And in the second situation, you can see if you draw tangents, it's negative to either side of the stationary point of inflection. So in these cases, you can either have one of two cases. Gradient is positive 0, positive, or negative 0, negative. Okay, so that's all the theory to do with stationary points and identifying which one it is. Let's look at an example of how to draw a gradient function using this information. Okay, so sketch the gradient function y is equal to f dash of x, showing the coordinates of any points where the curve cuts or meets the x-axis. So what I do first is, because we're drawing the gradient function, I draw a set of axes directly below it so I can compare what is happening. Now remember, when we're drawing this curve, it's going to be not y is equal to f of x, it's going to be y is equal to f dash of x. The first thing I need to do is identify where the stationary points are. So where is the gradient 0 and y is equal to f of x? So I can clearly see that gradient is 0 here at this point, and gradient is 0 here at that point. So these are my stationary points. So what I do know is if I draw a dashed line going down, then I know, because the gradient is 0 at that point, that means in my y is equal to f dash of x curve, it's going to it's going to cross the x-axis at that point. So that is at -1. Okay, similarly, because the gradient is 0 at x equals 1, I know that it's going to cross the x-axis of my y is equal to f dash of x graph will cross the x-axis at 1. Okay, so I know the x-intercepts are -1 and 1 because the stationary points are at my x equals -1 and 1. Okay, now I need to look at what's happening to the gradient in these three parts. Okay, so if I draw tangents in the first section of the graph, I can see that it's going up, so that's going to be positive. In the second part of my graph, second section of my diagram, it's going down, so it's negative. And my third part is going up, so it's positive. So that means if it's positive, when I draw it here in my in my second diagram, which is y equals f dash of x, I know this part will be above the x-axis. This part, because it's negative, will be below x-axis. The third part will be, because it's positive, will be above x-axis. Okay, now I know, again, if I'm drawing sketches in this part, I know it's going to be at this point, it's getting closer and closer to infinity, and then gets to 0. Here, same thing, it's going to be infinity here. So infinity there, infinity there. So if I were to draw this out, I know it's going to start off at infinity, positive infinity, and then it's going to get closer and closer to 0, because obviously it crosses at 0. So above the x-axis, that part. The second section of the graph is below the x-axis, so I know it's going to go below. At some point, it's going to turn around and cross the x-axis at 1. And then the third part of the graph is above the x-axis, approaching infinity, so it's going to go like that. So something along those lines will be my y is equal to f dash of x graph. Okay, so you can see above the x-axis, below the x-axis, then above the x-axis, and going through the points -1 and 1, because it's a stationary point. Okay, let's look at another example. Sketch the gradient function for the curve below. Okay, again, we need to roughly draw another axis directly below it. Okay, if I look at the stationary points, that seems to be a stationary point there. So if I were to draw one here, I know that I will have an x-intercept there, because the gradient is 0 at that point. Okay, there seems to be gradient is 0 at somewhere there. So again, if I were to draw a line going down here, then I know there I'll have an x is equal to 0, x-intercept again, sorry. And there is another stationary point there. So I've identified all three stationary points. So that means in my y is equal to f dash of x graph, there will be 3 x-intercepts. So there. Now I need to see what's happening on each of the 4 sections. So here, gradient is positive. In this section, let me use a different color. So you can see gradient is positive here. Here, gradient is negative in this section. Here, gradient is negative. Here, gradient is positive. So it's going to put positive infinity here, infinity there, and infinity there. So it's going to start off in positive infinity, it's the first part, because it's positive, it's going to be above the x-axis. So I know it's above the x-axis until it gets to this x-intercept. The second section of the graph is negative, but then it goes to zero, back to obviously 0.0. So that means it's going to do a curve like this, but all staying below the x-axis. The next part of the next section is also negative, going to the next stationary point, which is 0. So that means it's going to, whoops, undo, undo, undo. Okay. The next part of the graph will go again below the x-axis. So it's going to go something like this. The last part of the graph is positive. Gradient is positive, so it's going to be above the x-axis. So it ends up there. And this is labeled as the gradient function, which is y is equal to f dash of x. Now, if you wanted to summarize this, key ideas when sketching gradient function, if it's a minimum or a maximum, it means it cuts the x-axis. So any minimum maximum that you have, it cuts the x-axis. So if we go to the previous example, you can see at this point and that point, obviously it's a minimum and a maximum, and that is where the y equals f dash of x cuts the x-axis. If it's a stationary point of inflection, which is basically, if I change it to green, is that point there, then you can see at that point in my y equals f dash of x, it doesn't cross it, but it just touches it. So it bounces off it and comes back to the same side. Yeah. So it touches the x-axis. If it's a positive gradient, we've already discussed, it's above the x-axis. If it's a negative gradient, it's below the x-axis, because obviously negative means less than 0. Okay. And the two other scenarios you need to think about are what happens when it's a vertical asymptote and when it's a horizontal asymptote. So I'll go through those ones separately. So for a vertical asymptote, so imagine I have a graph like this. I'm just going to draw one. So imagine my graph looks something like this, where it gets closer and closer to this value here. So this is my vertical asymptote. So this is my graph for y equals f of x. Then if I were to draw the gradient function directly below it, then I can see that as x is getting closer to this number, x is equal to a, let's say, then the gradient is getting closer and closer to infinity. So your gradient function will also have a vertical asymptote at x equals a. Okay, so a vertical asymptote in y equals f of x also translates to a vertical asymptote in y equals f dash of x. And you can see clearly in this example, the gradient is always positive, but obviously it's getting more and more steep. So if I were to draw the gradient function, it's always positive, so but it's getting closer and closer to here, which is infinity. So this is y is equal to f dash of x. So in this example, you can see a vertical asymptote in y equals f of x translates to a vertical asymptote in y equals f dash of x. Now let's look at what happens with the horizontal asymptote. So if I have a horizontal asymptote, let's do just an example. So let me just write xy's everywhere. Okay, let's say we have horizontal asymptote at some value, I don't know, just somewhere here. Doesn't matter where it is, let's have it there. And it's going from infinity all the way, getting closer and closer to this value. Okay, so if I were to draw, so this is y is equal to f of x. Now if I were to look at the gradient function, okay, if I look at the gradient, I can see my gradient is always negative, but then as it's getting closer and closer to the asymptote, it's getting closer and closer to 0, which means I'm going to have a asymptote, because it's getting closer and closer to 0, but the gradient is never reaching 0, and that means y equals 0 is an asymptote in the gradient function. And because my gradient is always negative, and it's obviously more and more negative as x gets negative, that means it's going to be negative always, but getting closer and closer to 0, but never reaching it. So that would be y is equal to f dash of x. So a horizontal asymptote always gives you a horizontal asymptote in the x-axis. So it won't be in the same place. So do you see how the asymptote is is a positive number, obviously. Y is equal to a positive number in my example, y equals f of x. But here, when I'm drawn the gradient function, my horizontal asymptote is at the x-axis, and that is always the case no matter where the horizontal asymptote is. Okay, just obviously notes to help you out. Always draw the gradient function under the original function because you can clearly see what's happening and you can line it up. Identify stationary points and use this to divide into sections. This also tells you the x-intercepts of the gradient function. So I always section it up. Then I decide what's happening. Is the gradient positive or negative in each section? And complete sketching the rest of the gradient function. Always look at where it's infinity and where it's getting closer and closer to 0. It says, be careful with asymptotes. Look at how the gradient is changing. Is it getting closer to 0 or undefined? So these are the key ideas. Always use this guidance to help you to draw the gradient function. Let's look at a few more examples, a bit more complicated examples before. Okay, so let's look at this one, which obviously has an asymptote. Okay, the diagram shows a curve with equation y equals f of x. The curve has an asymptote at y equals -2 and a turning point at -3, -8. So that means this is a minimum point. So if I were to sketch this out, my gradient function is that sketch the graph of y equals f dash of x. Okay, so this will be part A, x and y. So because at -3, we've got a stationary point, that means when I draw my y is equal to f dash of x, then I know that -3 is going to cross the x-axis. Let's look at what is happening in the two sections of my graph. So I can see clearly that my gradient is negative in the first section and then positive in the second section, but then it's getting closer and closer to 0, so approaching 0 as x increases. So that means, so the first section of the graph will be below the x-axis because it's negative. So it's going to start below the axis and then it's going to hit -3. Then it's going to be positive. And you can see somewhere there's a point of inflection, but it's not a stationary point inflection. So you know that it's going to reach a peak at that point. Doesn't matter about that so much. And then it's still positive, but then it's getting closer and closer to 0. Okay, so that means there's an asymptote at y equals 0. So if I label it, there's an asymptote at y equals 0. So that's part B. Part B, state the equation of the asymptote of y equals f dash of x. So this is y is equal to f dash of x. So asymptote is at y equals 0. Sketch y equals x squared minus 4x plus 3 and the gradient function on separate axes. So if I have y is equal to x squared minus 4x plus 3, is the same thing as y is equal to x minus 3 times x minus 1. This is a quadratic curve crossing at x equals 3 and x equals 1. So if I were to sketch this graph, it's a positive quadratic, so x and y is crossing the x-axis at 1 and crossing the x-axis again at 3. So my graph would look something like this. Y is equal to x squared minus 4x plus 3, or you can call it y is equal to f of x. Then if I were to draw the gradient function for this, then I know there's a stationary point at x equals 2, because it's symmetrical Roomba in the middle. So at x equals 2. At x equals 2, it will cross the x-axis for y equals f dash of x. And if I look at the two sections of my graph, if you look at the gradient on this side, it's negative. Gradient on this side is positive, which means my first section of my graph will be below the x-axis. So below the x-axis, and then the second section of my graph is positive, so it's going to be above the x-axis. Y is equal to f dash of x. Okay, let's do another example, another easy one. So sketch the function y equals x minus 1 squared times x plus 1 and its gradient function on separate axes. So again, if I've got, this is a cubic, it's a positive cubic with x equal, with roots x equals -1, x equals 1 is a double root. Remember, double roots is going to bounce off it. So that means if I'm sketching this, which is y equals equal to f of x, let's say f of x is equal to x minus 1 squared times x plus 1. Then it goes through -1 to this curve, goes through, crosses at -1 and touches at 1. It's a positive cube, so it starts off at quadrant 3, goes up to quadrant 1, which means it'll look something like this, and bounces off 1 because it's double root. X and y, this is y is equal to f of x, and we can clearly see the stationary point is at somewhere here. Depends on where your stationary point. And somewhere here. Okay, so if I were to, depends on how you have drawn it basically. So x and y, so that means stationary point, because let's draw the sections in. So because the stationary points are at those points, we have x intercepts at those points as well in our graph for y equals f dash of x. If we look at the gradient is positive here in this section, negative in that section, and positive in that section. Which means when we draw this out, positive section is going to be above the x-axis, then it's going to be negative, and then it's going to be back to positive. So this is y is equal to f dash of x. Let's look at more complicated examples. So for each graph given, sketch the graph, the corresponding gradient function on a separate set of axes. Show the coordinates of any points where the curve cuts or meets the x-axis, and give the equations of any asymptotes. Okay, so first of all, identify the stationary points. So that point, and that point. So when we draw y equals f dash of x here, let me redraw that. So I know at that point, so let's draw lines going down. Because we're separating out the different parts of the graph. We know that those stationary points are x-intercepts on our gradient function. So that will be -9. That one will be 0. And this will be 6. If we look at different parts of the graph, gradient is positive here, gradient is negative here, positive here, and negative there. So positive means above the x-axis, and at each end, this is positive infinity, and here is negative infinity. So that means it's going to be above the x-axis, positive infinity as x is more negative. So it's going to end up looking like this. Between -9 and 0 is negative. It's going to end up looking like that. Between 0 and 6 is positive. So it's going to look something like that. And then between 6 and infinity is going to negative infinity. So it look like that. So this is y is equal to f dash of x. You can't clearly see, this is x equals 6. So it's -9, 0, and 6. Okay, so that was A. Part B. Okay, first, are there any stationary points? There are no stationary points. So that means our gradient function will not have an x-intercept. So we won't cross the x-axis. Okay. Okay, what is happening with the gradient? So there's going to be only one section of the graph. What is happening with the gradient is always positive, and then it gets closer and closer to 0. So positive throughout, and obviously this part it's tending to positive infinity, and this part is tending to 0. So that means it's all going to be above the x-axis. It's going to start off at positive infinity, and then it's going to get closer and closer to 0, but it's never going to reach 0. So that means there's an asymptote at the x-axis, which means asymptote at y equals 0. Let's look at C now. So again, sketch. Okay, let's identify the stationary points. Are there any stationary points? You can see the stationary point here, which is at 4. So let's enroll that stationary point in, which is at 4. So we've cut the x-axis at 4. What's happening with each section of the graph? Okay, so here I can see the let's see if we go back to red. Here I can see the gradient is negative. Here I can see the gradient is also negative. And the gradient is also negative here. Going to negative infinity. Here it's at negative infinity. Sorry. Negative infinity, negative infinity. Okay, so if I were to draw this, all of these, that means for my f dash of x graph, everything's going to be below the x-axis. So it's going to negative infinity. Here it looks like it's getting, you can't see enough of it, but you can see it's getting closer and closer to 0, yeah? So possibly it might be getting closer and closer to 0, but we don't know what's happening. There's definitely going to be an asymptote at x equals negative 7. So x equals negative 7. X equals negative 7 is also an asymptote. So negative starts off negative, getting closer and closer to negative infinity. So like that. It's negative infinity again here. And then getting closer, obviously at 4 it gets to 0, so it's going to be something like that. And then again it's negative after 4, the gradient. So it's going to be below, but it's getting closer and closer to negative infinity as x increases. So something along those lines is the gradient function. Okay, let's look at these examples. Okay, first thing I need to do is let's draw the axes below. Okay, identify the stationary point, so it looks like it's there. Stationary point at here. And this part I know is getting closer and closer to, tends to 0, yeah? So that means if I'm going to split it up into 3 parts. So it crosses the x-axis at -2 and 0. The gradient is negative in the first section, positive in the second section, negative in the third, and then getting closer and closer to 0. Okay, so if it's negative in the first section, it's going to go from negative infinity and get to 0 at x equals -2. Then it's positive from 2 to 0, so it's going to do a curve like this. And then it's negative. Negative, and then getting closer and closer to 0, so there. So that means there's an asymptote. Maybe do it in different color. Asymptote at y equals 0. Something along those lines. Y is equal to f dash of x. Okay, E now. So if I were to draw the gradient function below it, and because at x equals 6, there's an asymptote, and it's getting closer and closer to infinity and negative infinity, I know there's also going to be an asymptote at x equals 6. There are no stationary points, so there are not going to be any x-intercepts. So let's see what's happening on each part of the graph. So I can see the gradient is positive on this side and still positive on this side. The only thing is I can see on this end it's getting closer and closer to 0, and this end is going closer and closer to positive infinity. Here it's getting closer and closer to positive infinity, tending towards positive infinity. Here it's tending towards 0. It's getting more and more flatter. So if I were to sketch this, I know it's going to start off, get closer and closer to 0, and then as it approaches the asymptote, it's going to get closer and closer to infinity, like that. Okay, on the other side of the asymptote, I know it's going to get closer and closer to first positive infinity, and then getting closer and closer to 0. Okay, so there's an asymptote at x equals 6, and there's also an asymptote at y equals 0. So this is y is equal to f dash of x. Last one, which is f. If I were to sketch this one, so I can clearly see there are no stationary points, so we won't cross the x-axis for y equals f dash of x. I can see the gradient is always negative, everywhere negative. At this end, it's getting closer and closer to 0. Oops, let me not write it like that. So here it gets closer and closer to 0. Here it gets also closer and closer to 0, the gradient. So it's always going to be below the x-axis because gradient is negative everywhere. At extreme ends, it's going to get closer and closer to 0. That means it's going to look something like this, because at each end it's getting closer and closer to 0. So that means there's an asymptote at y equals 0, and this is y is equal to f dash of x. So you can see it can get quite complicated, but just use the rules that I've told you about to obviously help you to answer the question. Okay, there's one more I'm going to go through, which is sketch the gradient function for y equals sine x. So if I were to draw it only from minus 360 to 360, so this is x and y. So I know that the sine x graph goes from 1 to minus 1. So if I were to, so 360 to minus 360, starts off at 0, goes up to 1, back to 0, minus 1, 0. Similarly on this side, minus 1, 0, 1, 0. So this is equal to f of x is equal to sine x. So y is equal to f of x. So if I were to, where are the points of intersection? Sorry, where are the stationary points? Here, 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 and here. So let's partition it out. So that means the gradient function for y equals sine x would have x-intercepts. So if I label it from 90 to intervals of 90 up to 360, that means it will cross the x-intercept at minus 270, minus 90, 90, and 270. So draw this line to help me out later on. Okay, and if I look at the gradients, it's positive here, negative here, positive, negative, and then positive. So if I were to sketch it out, first part is positive, then it's negative at some point going back up, then it's positive, going back up, and then it's negative, then it's positive. So this is y is equal to f dash of x. And you can see this graph should look familiar. It looks like the cos graph. So it does give you cos x graph. So that means if f of x is equal to sine x, f dash of x is equal to cos x. Okay, there are some conditions involved with that, but we won't go into that right now. Okay, let's do y equals cos x now, similarly. So cos x graph. It looks like this. Rough sketch. Stationary points are here, 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 and here. So that means when I'm drawing my y, so this is y is equal to f of x, which is equal to cos x. So if I were to sketch my gradient function, and that means it's going to cross it at 0, 0, 180, 360, minus 180, minus 360. Okay, and if I separate up my sections of my graph between stationary points, then it's negative here, positive here, negative here, positive here. So if I were to sketch this out, first section is negative. So it's negative. So it looks like this. Then it's positive, which is this. Then it's negative, which is this. And then it's positive, which is here. Now this looks very familiar. It looks kind of like the sine x graph, but it's been flipped along the x-axis. So the mirror line is at the x-axis. So that means it's the same thing as multiplying sine x by -1. So it's because it's a reflection of the sine x graph along the x-axis. So that means if f of x is equal to cos x, then f dash of x is equal to minus sine of x. And we look at that again when we look at differentiation with trig functions.